başlayamadı. Hiç fazla zaman kaybetmeden Sayın Doktor Keyvan Firuzi'yi takdim etmek istiyorum. Kendisi doktorasını ve doktora sonrası çalışmalarını Sharif Üniversitesi'nde İran'da tamamlayarak bölümümüze yeni katıldı. Yüksek voltaj alanında çalışmalar yapıyor ve de bugün onu dinleyeceğimiz için çok mutluyum. Kendisine bırakıyorum.
Teşekkürler. My name is Keyvan Firuzi, and I recently joined the high voltage laboratory in the METU. The topic I'm going to present today, I will first try to talk about high voltage engineering in general, to give you some idea about high voltage engineering, and I will talk about the recent research in this area. You can hear me, right? Okay. Let me. You do the recording or I do the?
We are recording now.
Okay, great. The topic I'm going to talk today is about online monitoring. Specifically, we're going to talk about monitoring of power transformer, mostly using partial discharge. But before that, as I said, first I'm going to talk about high voltage engineering, so you have some idea about what it was, what it is, and what it will be, high voltage engineering. Then we will talk about the recent topics, which is online monitoring, which deal with many different topics like sensor fusions, how we do this extreme type of data processing, and how we are able to identify different types of faults. In order to understand what it means, high voltage engineering, it is we have to mostly generally understand how we run a business. It is more general than just the high voltage engineering. We are talking about the whole industry. One of the most important topic in the industry is how we do this maintenance, how do this maintenance management. The first idea when we started to using these machines in our factories was to use this idea of reactive maintenance or run to failure. When we buy a device, we buy a motor, we put in a service, and after it failed, if we can repair it, we will try to save it and use it. But most of the time, we weren't able to use it, and we usually throw it away and buy a new one. Of course, as a result of this strategy, the production cost was very high, and the device we manufacture was very expensive. After some decades, especially around World War II, because of its very special condition, people started to try to cut the price. And the main idea was how we can use our assets in a more effective way. Of course, we don't have lots of money to buy new devices. The core idea is how we can use our devices in a more better way, how we can increase their lives. In order, as a result, we cut the production's cost. The idea was to use this preventive maintenance. We do this maintenance before it fails. But the problem was we don't had any idea that when it's gonna fail. So the main approach was let's use our experience, our previous experience, and set a time period that we have this kind of feeling that it's gonna fail. For example, for different machines, we had this like 6 months maintenance, 1 year, 2 year, based on different types of device and the experience we had before. It wasn't very exact, but it was the best approach that we came on that time. So as a result of this new approach, some of our problems start to reduce. Okay, we will be able to increase the useful time of our machines, and as a result, we were able to cut the price to some level. But some problem also start to grow. I think in around 1970, they did some kind of survey that to evaluate the effectiveness of this new approach, and they figured out that some new failures start to grow after they implemented this method. And the problem was because of these human interventions. Every time we want to do this maintenance, some people should do it, and from time to time they made some mistake, left something there, and as a result of that, we started to have this weird type of failure. And other problem was we really didn't know that what's wrong with our device. So we had to do this overall check, and by the overall check, these devices can be very large and very complicated. For example, a generator that we usually do this kind of maintenance from usually 1 year, it takes like 3 or 4 weeks to do this complete over checking of every component of it. So every time that we get this device out of service, it usually takes lots of time to bring it back to the service. And also, because we bring it out of the service and we made some change to this device, we cannot just turn it back to the power system, because we made some change and we had to do some type of test to make sure that its situation doesn't change. And the third idea, which we had this idea from before, but we didn't have a tool to predict when this device is gonna fail and when it's appropriate time that we have to apply this type of maintenance. This idea of predictive maintenance, that we start to do some measurements and predict that when it's gonna fail and how it's gonna fail, what's the problem, not just the failing time, but also the type of the problem we are dealing with. So we can apply this type of maintenance in an appropriate time and with a very deterministic approach that what we are going to repair. So as I said, this is a general idea, and there's a huge application for this predictive maintenance. Airplanes is investing huge amount of money to predict that when their plane is gonna have some kind of problem, and they apply this maintenance in an appropriate time, because it costs huge amount of money to do this maintenance. And as I said, also when you are trying to apply this type of maintenance, it usually takes lots of time for a plane, because it's a very complicated and huge device. You don't have access to it like months. So the idea and the strategy is to do this predict the situation of the device and apply this type of maintenance. But as I said, it was the original idea. It was we had this idea from before, but we didn't have the tool to apply this method. But the situation changed in the recent years. We are deploying very different types of sensors. Our chip and our processors become much more powerful than ever before. We have access to the cloud or this algorithm, this machine learning algorithm. All of them came hand in hand to make this predictive maintenance possible. So from this general idea that how we run the business, so let's go to talk about how it's affecting high voltage engineering. So if you want to do this run to failure idea in a power system, we have lots of equipment in a power system. Before we using them inside the power system, we have to test. So we need a laboratory for testing these huge devices. And it's even though we had these laboratories from the beginning around the 1900, but it is still growing and there's a new challenges. We still increase the voltage level in our power system. We go to this ultra high voltage. You can find 1100 kV power systems in China, for example. And if you have this level of voltage in power systems, when you want to test it, you have to go even further. You have to test it with the twice or third time of this voltage. So generating this level of voltage is very challenging. The second type, which I think is even more important, is this idea of SVDC system, that we are bringing more and more these power electronic type devices to our power system. Our power system is not this old type of system, and we are using these different type of thyristors, IGBTs, all that electronic device are becoming more and more prevalent in our power system, which introduce a new types of problem. And for testing them, also they become, since they are become a part of our power system also, we have to game up with this new idea of how we're gonna test them. We need to develop new voltage level, new current shape in order to test them. So even though we have this for the first time, for the first step is to have this high voltage laboratory, and we have them for more than a century. They still need to, still need to do a research in this area and develop a higher voltage and new type of voltage shape to test our devices. So that's the first idea. But the second idea, that we start to test our devices in a power system. For example, we take out our generator from service and we do this maintenance. But before bringing it back to the power system, we have to test it, because we made some change and we consider it as a new device. And for every new device in a power system, we have to test it to make sure that it's in a good condition. But the problem is we cannot bring the generator or transformer to a laboratory, test them, and bring it back, because they are very, very big devices. They are very huge, and it costs very, very high money to do this operation. So the idea is to apply this type of voltage and current in a site, not in a laboratory. In a laboratory, we have this huge space, and since we are not moving our devices anywhere, we really don't have to worry about this kind of concepts. But in an on-site testing, since these devices become portable, they have to be more compact, and we have to be able to bring them everywhere, because they are outside and they can have lots of different type of dangers on them. So the sturdiness is become even more important. So in order to get this level of compactness and portable, we also have to come up with this new idea of generating high voltage and high current, which is mostly based on this power electronic switching device that makes to generating these types of voltage and current in a small scale possible. So we high voltage engineers not only affected by this power electronics application, but we also use them to generate different types of voltage and current for on-site testing. That's the second approach, which become very prevalent in the past 1 or 2 decades, and many startups came up with new idea to generate a new type of voltage to test them in this type of device in a site. But the third idea, which also is one of the most important idea, is this online monitoring, which makes this predictive maintenance possible. The good news is that in online monitoring, we don't need to generate a very high voltage or very high current, because these devices are already connected to the network. They are working, and we are trying to do some measurements in order to understand their situation. The core idea here is to do measurements and also do a process. In a sensor side, we have all these different types of sensors: resistive, inductive, capacitive, acoustic, even RF, measuring these electromagnetic waves. Optics recently become one of the most important way of measuring these voltage and current in a much more compact and much more resilient to the noise. Then, as I said, we have this processing, because which is become much more possible in these recent years. And our DSPs or FPGAs become much more powerful than ever before, and make it completely possible to apply these type of methods in the real applications. And after recording this device, we need to process them. And signal processing, machine learning, and all that algorithm is also become much more important in this new type of online monitoring. One of the most difficult concept and idea about this monitoring is because usually our data has a very high frequency, and because of that, we have to do a very high level of sampling. For example, in RF measurements, we go around 5 gigasample per second, which produce huge amount of data, and we cannot store this data and process them later. It's not just possible. So we have to start using this idea of stream data processing, which we try to process this data without storing them, and we only store the useful information. It's like compressing the data. We have this huge amount of data, and we have this real-time methods and techniques to reduce this volume of this data, which is usually the filtering as a real-time processing. And we have lots of noise, because in this real application, all these devices are connected to each other, and there's lots of noise source that we should be able to deal with them. How we are going to identify the type of the fault we have. Because as I said, one of the approach and one of the goal is not only identifying that there's something wrong with this device, also understanding exactly what it is, which part of this device has problems. So when we bring it out, we only just concentrate on that part, make our repairment just as fast as possible, and bring this device back to the service. So this device defect type identification also become very important, which is mainly and basically is based on the database we develop as some kind of idea that we develop this database for different type of fault, and later on we try to compare our data with this reference data to get some idea about the possible defects. And also, because we are able to store this data, we can do this trend analysis, which makes this predictive maintenance and also called condition-based maintenance much more possible. Through just looking at the trend of this data, we can have some idea that when it's gonna fail and when it's appropriate to do this maintenance and increase its useful lifetime. So in a power system, we have lots of devices. We have generators, cables, transformers, GIS system, gas insulated substations, which every one of them is very important for us. And because of that, it's worth spending money on increasing their lifetime and also knowing their exact situation to have a higher reliability power source. And how we are going to apply this online monitoring is through applying different types of sensors on each of these devices. These sensors can be different from device to device, but we usually apply more than one sensor, usually lots of them, like 7 or 10 different types of sensors to do all these type of measurements, not only electrical, but mechanical and also thermal measurements. Usually electrical measurement is the most difficult one, because in the thermal and in this mechanical measurements, the variation is much slower, and our sampling data and the data we are dealing with is much more simple. But in electronic, and when we are dealing with electromagnetic waves, we have to apply this very high sampling rate. We have the problem of very huge data, and how we are going to deal with this level of data is very challenging. But by applying these different type of sensors, we are transforming our simple like power cable to a smart cable. The only difference, the main difference between the smart cable and the usual cable we had before is they have these lots of sensors applied on them. But how we exactly do this online monitoring, beside all this general idea? In order to give you some idea that how we are going this, of course, all of these devices is very important, and each of them considered as a one big project. But here I'm only just kind of focus on the transformer as one example that how we do this online measurements, online monitoring. So, in order to do this monitoring, one simple things that we should know about power system equipments is that they mostly created by insulators and conductors. Their basic construction is two different type of material. We have conductors and we have insulators. Conductors usually, it's very rare that we encounter some type of problem inside conductors. Of course, I'm not saying it's not possible. It's impossible, but the rate of the problem we usually have with conductors is very, very low. Most of our problem is with insulators, the part that have this duty that prevent following current in a certain directions. They usually encounter with lots of problems, and they are the main source of the problems in our power system equipments. And how we are going to monitor the situation of the insulators, we had this idea from like 4 or 5 centuries ago that the best method is using this partial discharge measurements. When they have some problems, they usually start to producing these partial discharge signals. One method to measure these signals is what we call IEC standard measuring impedance. We measure this impulse current generated as a result of this impurity inside these insulators. We are applying this type of measurements for more than 3 or 4 decades. So we have lots of experience in this type of measurements. They can be easily calibrated, which is very important for us. And their data type is very familiar to us. By just looking at their data type, we usually are able to even specify the type of the faults we have in our insulators. But they also have lots of problems. One of the most main problem of this type of measurement is that they have very high level noise, because we are directly connected to these high voltage systems. They usually have lots of noise. And the other problem is that if we have lots of problems, it is very common for an old devices that they just don't have one type of problem. They usually have more than one type of problem. And in that case, we usually encounter, we cannot interpret the data we are getting from this sensor. The second idea, which is a more recent one, is to, as a result of this impurity, and when this discharge happens inside these insulators, not only current is generated, because these are very fast moving electrons, and they also produce a very high frequency electromagnetic waves. These electromagnetic waves can get as high as like 2 or 3 gigahertz inside these devices. The main advantage of this device, because we can go at higher frequency and measure this signal at much higher frequency, which are far above from the type of the, in our power system is 50 hertz, and some disturbance, they can go up to like 10 or 20 megahertz, the type of disturbance we have in a power system. But from higher than that, we usually don't have any type of source of disturbance. And the only type of fault that can go as high as like 1 gigahertz is that these partial discharges generate as this type of impurity. So by just going at these higher frequency measurements, we are getting rid of this noise. And also because the type of the signal that generated in this case is a wideband, they are not very similar to what we have in this communication system, that they are very narrow band. Our signal is very wide band, which makes us possible that to sweep this frequency and escape from noise. But they have problem also. We cannot calibrate them, and because of we are getting them from this electromagnetic wave, and this electromagnetic wave is dependent on so many parameters, like the structure of the device and where is the source, how all these bouncing wave is working. It's very complicated, and interpreting this device, this data is also very complicated. Our idea was that let's use this type of measurement at the same time and fuse the result. By this sensor fusion idea, we start to measure from 2 different sensors and get this most result, because one's advantage is others' disadvantage, but putting both of them together, we can get the most result out of it. But after we applying these different type of sensors, for example, here for this transformer, I introduced 2 different type of sensors, but for the generators or cables, these sensors can be different. But we usually, as I said, we have more than 1 sensor, and we usually came up with this idea of sensor fusion. But after that, the other challenge is that when you are doing these RF measurements with very high frequency, you cannot apply these offline type processing. We need to analyze this data at the real time, and we cannot store this data. We can only store a very limited volume of data, which is the result of our processing. So the solution, of course, it's a developing area in this other area, but we just use these new techniques we have in this data processing scheme. That we use this stream data processing. We don't, and the first one is that it should be real time. We cannot spend any time on this processing, so it should be in a real time. And we cannot store the raw data. Of course, we can store the results, which usually have a much less volume, but our raw data, especially, it's very hard to store them. And one other important concept is that even we reduce the amount of the data, they should be somehow constant over time. Our result, they should not also get very expanded over time. The data processing, stream data processing, usually have 2 main stages. One is, as I said, is called online phase, that we do this real-time measurements, real-time processing, which the main idea is that to extract some type of features that make us to do this noise canceling, and as well as these different types of problems separation. Usually our filter, for example, we apply one bandwidth filter around 10 megahertz, the other around 20 megahertz, and we can apply it because it's a real-time process. But after doing this online phase, we also need this offline phase, in which we do this further analyzing on our stored data, which the amount of the data is much less time. And in the offline phase, we usually have access to much stronger source to do the very complicated type of processing. How it's related to this new idea? The new idea about this preventive maintenance is we have sensors we installed on these devices, and we do this edge computing, that we do this low level of computation on our data, bring them to reduce their amounts and save as much information as possible. And after that, we usually, in this new idea, as I said, we send this data to the cloud. this is something that happens right now, and I take this image from this GE's website. They are investing lots of money on this for near a decade. The idea, so we install these sensors, and we have this edge computing, FPGAs, DSPs, all these devices making this low-level computation, and after that we send this data to the cloud. So now that we are in the cloud, we have access to the huge resource that we can store this data over time. So we can make this trend analyzing, and also because we are in this cloud, we have access to all these machine learning, deep learning, and all that different algorithm to process this data is even further. And the method we developed based on this online phase and offline phase is because we want to get it in a complete coherence with this idea. We want to apply this online phase algorithm in our edge computation, and in our offline phase, which is much more complicated, we are doing all these image processing, all this stuff, which usually also needs lots of resource. We do this type in our clouds. The one example, of course, we didn't have access to the cloud, but we just stored the data and analyze it inside the laboratory. For the transformers, when you are inside this laboratory, we usually came up with this idea of how to make a much more compact one that we can still use it, apply different types of faults, make all these measurements, and somehow get the similar results to the actual case before applying it in a real-time world. One case that we did, we applied this three-phase small-scale transformers, and we start to deploying different types of faults inside of them. We try to introduce different types of noise, which we usually have in a real-time application. And then we start to record and evaluate our algorithms. Because especially in our power system applications, at some point we should go to the laboratory and test our algorithm with this real data. Even it's like a first phase in the testing our algorithm. And after making our corrections and make our algorithm even robust, then we go to this real application and do these pilot measurements. But before that, we have to evaluate our algorithm in these laboratories. That's one of the other reasons that we still need these types of laboratories, because every new ideas, every new devices, they have to be tested inside this laboratory. We cannot just go to this power system. They are very expensive, and it's not very easy to access these type of devices and do every type of measurements. So we start to applying our algorithm in the online phase. We apply these filters and somehow compress our data in a single matrix, basically. Because our final data was in the form of the matrix, its volume didn't grow through time. It just only get updated through time by just getting this new data. And in the offline phase, that we had time, and we can easily start to compare our data with our database, or start to separate them, apply this new image processing, all that algorithm. But the real time is still working, it's still updating, but from time to time we get this data and do this further analyzing. As I said, I didn't want to go so much deep. I just want to give the general idea that why we are doing this type of device, and when we looking from its application, it's growing. It's not completely applied, or we are completely using it inside our factories, but it's happening. As I said, big companies are making lots of investment on this idea, and it's the new big event that people call it as an industry 4.0. That is the new level of optimization in the generation and making this device and our production even cheaper. If you are interested, you can look at some of the publications that I had in this area about online processing, and especially most of them was related to the transformer. As I said, when you are going to deeper to these devices, each of them has problem related, and you cannot just at the same time focus on all of these devices, even though there are similarities. These stream processing, these clouds, all that are very similar, but especially in the sensors and type of processing that we have, they usually are very different. So I hope that I didn't speak too long. I wasn't looking at that. So I hope that it was clear and somehow give you a good information about the high voltage engineering and also very important topic of preventive maintenance.
Thank you, Dr. Firuzi. Your talk was perfectly timed and it was very, very interesting. I'm sorry about the late start again. Now we can take questions.
Okay, great. It's a very broad topic. You don't have to really be a high voltage engineer to talk about this.
Yes.
If you are doing this data processing or you are working in another field, I think you can still have some questions about this. These are very...
maybe I can warm up people because I have a question. I can ask my question first, maybe then other people can... I volunteered to ask my question, even though it may be a very elementary, stupid question. So, so when you detect this partial discharge, at what point do you do something about it?
I didn't get it. So
suppose you detect partial discharge. You realize that there's a discharge problem in the transformer. How bad is it before you do something about it?
It's about, as I said, doing this right thing at the right moment. We are not trying to prevent it from happening. It's happening, and we are going to do this maintenance. We are going to remove it somehow, but we are going to, the idea is to do it in a perfect time. And also, when we are going and opening this transformer, they are very big devices. We are just going to look at some specific part that we know it has a problem, and we are just going to remove that part and replace it with a new part. There's no magic here, but we are just trying to do this right thing at the right time and increase the volume of the time we are spending on this type of repairment. For example, in a cable, I think it's more clear. We have this cable and we find there's a problem. We usually locate where is the problem and we just cut that part and replace it with the new one and continue our life. I mean, that's how we do our actions. That's how we repair it.
I see. So my other question is, how does Industry 4.0 come into this? So you mentioned there are some certain sensors, and these sensors send data to a cloud-based processing.
Yes. The core idea about Industry 4.0 is this preventive maintenance. When they define this, what's the Industry 4.0, the main idea is that after making this digitization in our industry, its next step is to use this data to make a better asset management. The core idea is they call it asset management or preventive maintenance. All of them in a concept is very similar. And they are main concept of this Industry 4.0, which is aimed to get a new level of optimization in reducing the cost of production. I didn't know, is it answered your question or?
Yes, it does. Hello? Can anybody hear me?
Hocam ben duyabiliyorum.
Okay.
You can ask your question in Turkish, but if I can't answer it in the Turkish, I'm sorry, but you can ask it in the Turkish. I have no problem. I can talk a little bit.
Can I ask one more question?
Yeah.
So I guess with Industry 4.0, this monitoring is continuous and automated.
Yes, of course.
And I'm guessing some AI techniques come into the picture at some point.
Yeah, as I said, when we are storing this data in the cloud, the main idea is this AI techniques. We apply this AI technique inside this cloud. Companies like GE is cooperating with Microsoft in order to store and also evaluate and use their AI algorithms. And there are other companies as well, like Amazon. Nowadays, they are not only, we have cloud not only is a place to store our data, they also offer different type of algorithm to evaluate your data in a further step. So they also buy this algorithm from these companies like Microsoft to analyze their data. It's a very common right now for in a gas and oil, especially in the oil industry, is one of the first industry. In a power system is a little bit more difficult. Our devices is not, and the type of the sensors we are using is usually much more complexer than them. They usually measure the mechanical data or this thermal type of data, which usually are much easier to interpret, and they really don't need these lots of edge computations. Their data is not, they can send this raw data to the cloud. It's not going to take lots of space. But when it comes to the power system, there's lots of, in a sensors, we still have some problems. We are trying to solve them, but it's getting to where that it become very widely used in all of the world. But it's not as fast as oil or gas industry.
Can I ask something? I'm sorry if I'm wrong, but like at this point, it seems like you need a lot of sensors to implement to the systems, which probably takes a lot of money and a lot of infrastructure. So what I wanted to ask is, at this point of your research, does it cut the cost of not doing it, or what I mean, like, if you don't do this, will it cost more, or doing this actually costs more at this point? But
as I said, right now our strategy is to use this preventive maintenance, which we usually do this service from year to year. It costs a lot, and if you go to, there's lots of survey that I've been talking about this huge amount of money that we are spending on them. And as I said, in some cases, it usually end up having more problem than before because of these human mistakes and other things. So it is very important, and it's absolutely worth spending money on them. And there are also, we have to do this type of study, and sometimes it can be more complicated than this, because power system is a national interest. It's not somebody's assets. And for example, the companies like GE, as I said, in the US, they are improving in this area very fast. And most of the countries do not prefer to give all their data and the situation of their industry to the other companies. So it's very important, even from this national point, that we start this sooner than it gets very late, because at the end, even if you have this very sophisticated technology that can do all of this, maybe at the end the government don't want to give this allowance to another company to access to whole situation of its industry As you can see, if we are doing this measurement only on one device, yeah, of course we can. Even right now, there are some companies that install this type of sensors on one device, and they send this data to their centers and do this further evaluation. There's nothing complicated about that, but this can be very complicated in a system level. Suppose that we install these sensors in all of our equipments and send all data to a unique center in somewhere in the world. It can have lots of consequences. It is not just if you are thinking of in a system level, the problem that grows and the concerns and benefits is much more than just one single devices. So if you are thinking from single device perspective, maybe you end up with this result that you don't need, and maybe its benefit is not that much. But from this system level perspective, it has huge consequences.
Okay, thank you. Like, I just wanted to be clear. Like, I think this research, like, it is really bright. I just wanted to ask about the points.
Yeah, I know, I understand.
I have one question.
Okay.
It's okay. Hocam, what is the succession rate of predictive maintenance algorithms now? Since it is huge and real time, I thought it could be like weather forecasting. Similar to.
As I said, honestly, it is much more complicated in a power system application, but in another industry, they get very high result from this. It is not something that grows from the university. It is completely the opposite. It's the need of the industry that forces the universities and other research area to go in this direction because of huge benefits of it. But from the success point of view, we are implementing this type of idea right now in the industry in some level, in a very limited level, and people see its benefits. But the full picture that where we are now, and for example, we had this idea of automated cars, and we didn't know that how they are going to operate until Tesla came and they started to use this type of device, and they have like 1 or 2 fails, and which resulted in a human death even. But in order to get this clear picture that where we are now, we really need to apply it in a more broad sense. Right now, we are using it in a limited scale. Some of our techniques that I taught here, some of them even get really industrialized. Some of them get industrialized. For generators right now, we have some monitoring systems. Right? Usually, you know how this AI system develops. They say that, you know, you are gonna keep your jobs, and the AI is just here to give you some result. But after we getting all this feedback from this AI system, we usually replace it with the human. That's where we are now. For example, GE has these centers that gets all this data, and they make this automated processing, and also they have some technicians that looking at this data. So right now we have both of them, but we know their story. Gradually, we're gonna replace the human with this technician with this AI, at least to some level.
Thank you.
Can I ask one more question? Maybe it is the last one. I wonder whether we can apply those sensors and regarding processing like online monitoring, data processing, etc. The facilities currently in use. I mean, these opportunities are very welcome for the new sectors and facilities, but how about the already used ones? Is it possible, or is it a problem?
I didn't get your last part. Sorry, if you can repeat it.
Oh, sorry. I wonder whether we can set those sensor and remaining structures for the currently used facilities. I mean, is this propose a problem for this sector?
You mean we have already some sensors, and can we use them for getting this result, or installing these sensors create a new type of problem?
I think she means, can these sensors and measurement systems be installed in already existing facilities?
Yeah, I mean,
yeah, of course.
A bit older one.
I get it. Of course, the idea is that we develop of course, there are some idea that we cannot apply for the existing devices, and they should come up with these new devices, but they are very rare. Most of the industry prefers to, because in a power system, for example, if you have a power transformer, they usually last for 14 years or 15 years.
Yes, exactly.
We cannot wait them until they get out of the service, because the main idea that asset management, to take care of what you have right now. And we are not trying to develop a new type of transformers which takes longer to fade. We are trying to take care of what we have right now, and as a result of that, we decrease all these costs. So the main idea, even though there are some ideas there are some sensors that we can only apply them on the new devices. Most of them is about the type of the sensors I talked here. They are the type of device that we can easily install on a available transformer, for example. That's the main idea.
Okay, thank you.
Özge, Eren has a question. Would you like to ask that, Özge, or shall I ask it for you? So Özge is saying RF measurements, sensors based on RF signals cannot be calibrated. Why? Can you give some examples of these sensors? Özge's microphone doesn't work, so I'm asking instead.
Okay. As I said, when we are doing these RF measurements, since we cannot predict how they are going to behave, under different conditions, they're going to behave differently, because when we are in this very high frequency inside this structure that didn't design for that frequency, and depending on where is the source and the type of the structure, they can be very different from one manufacturer to the other manufacturer. All of this makes our measurement completely unique. And since we cannot predict all these very complicated, of course, there are some people still trying to make this calibration, but today speaking, even in this research area, and some people even proposing that it's completely impossible, but some people still hope that we can somehow figure out this complexity and makes it possible to do this calibration. Because if we can completely understand the physics of the behavior and how all these wave operating inside these devices, we can do some level of calibration. But right now, we usually consider them as a type of the signal that we cannot calibrate. They are not very similar to the electrical method that we have these simpler methods, simpler models that we can, based on them, we apply these calibration methods. They are much more complex than that.
Sheer bandwidth is a big challenge, it seems, and you're saying the frequency can go up to 2-3 gigahertz.
Yeah, of course.
And you don't really know what you're looking for. As you said, it differs from system to system, I guess. So.
Yeah, but since I think you are a communication engineer, I just want to tell that since when these source start to emission this type of waves, electromagnetic waves, the type of the sources also can be effect on this type of the signal and even their spectrum we get. So it's much more complex than that. We don't know lots about source and how it's traveling. The path is very unclear. and all of them makes it very challenging.
Thank you so much. Any more questions? Okay, I guess there are no more questions. We thank the speaker again, and we are ending the recording. I will say a few things for the 690 students as an announcement. As you know, you are asked to attend these seminars as with a camera on, if possible. Please try to arrange that, because that's a way we can see that you are attending and participating, and it's good for the speaker as well. It's encouraging.
I'm sorry, my camera is broken, so I couldn't turn it on for this seminar, but I will manage it.
Okay, and after the seminar, we're asking you to submit a short report after each seminar. You can submit it under the assignment tab. You can summarize what you got from the talk and give a critique to the speaker if you'd like. Okay, any questions? If not, I thank Dr. Firuzi again and, for giving the first seminar of our course. And I'll see you. Next. I'm very sorry about my lateness today, tardiness, and next week we're again meeting at 1:30, and our speaker is going to be Ali Matouk from Supelec, Paris. He will be talking about a new concept in designing random access wireless protocols. Okay, bye-bye then.
Thank you.
Thank you.
Bye.